We're going to start with something called the thermal radiation view factors, capital F, because chapter 13 is has a engineering bent to it compared to chapter 12. Chapter 12 talks about the properties of surfaces and how radiation is distributed with wavelength and band emission. It's got a little bit of a bent to physics to it. Chapter 13 has a much stronger content in engineering because we want to find out, for instance, how much radiation leaves one surface that gets to another surface. So the view factor is something important that allows us to make those kind of calculations. We start out with two surfaces, A1 and A2. We show a small differential area on those two surfaces. It's connected, the centers are connected by a distance r. R is the distance. And the angles of A1 and dA1 and dA2 with respect to their normals going to the distance r, theta 1, this angle, theta 2, this angle, from the normal to the line labeled r. Now, to do that, to find that energy between A1 and A2, we can say that Q from A1 going to A2 is equal to the view factor from A1 to A2, A1J1. Now, I'm going to define F A1 to A2 is a fraction of energy leaving surface A1 intercepted by A2. Sometimes you could say it's received by surface A2. Either one's fine. But that's the fraction of the total energy leaving A1, the thermal radiation energy, that ends up getting to surface A2. You can say it's intercepted by, received by, strikes by. They all mean the same thing. Maybe if FA1 to A2 is 0.10, that means 10% of the thermal radiation leaving surface A1 ends up at surface A2, 10%, 0.10. We take shorthand notation here rather than FA1, A2. So FA1, A2, we call that another shorthand notation F1-2. We know that to mean that's the fraction going from surface A1 to surface A2. We even simplify that further. We don't like the dash, so we just say F12. That's not F12, don't say F12. That's F12. It means the fraction going from A1 to A2. So we can rewrite this expression for, what's Q? Q is the amount of radiation in watts, just so you know. A1 is meters square, J1 is watts per square meter, and F is a fraction, and fractions are dimensionless. So Q's in watts. That's the number of watts going from surface A1, going to surface A2. So now the new equation is Q12 equal F12 A1 F12 J1. All right, so that's our equation there. Now, officially, the definition of F12 is this, mathematical definition. So that is mathematically how we define F12. It's derived in the textbook, in a whole page of the textbook. We're not going to spend the time to derive that. That's the result of the derivation. You can see that it's only a function of geometry. The distance r, cosine theta 1 and cosine theta 2, dA1 and dA2. It's only a function of geometry. The view factor F12 is sometimes called the geometric factor because of that reason. Okay. Now we can play the reverse game. Q from 2 to 1 equal F2 to 1 times A2 J2. That's the fraction of energy leaving surface A2 that is received by or intercepted by A1. That's Q21. In that equation, F21, 1 over A2, integral and then you can compare these and draw the conclusion. Since the double integrals are identical, don't forget, you can change the order of integration. Doesn't matter which cosine's first, theta 1 or theta 2. It doesn't matter which dA is first, dA1 or dA2. You can change the order of integration. And so the conclusion is, oh, you know what? If I multiply A1 times F12, that's equal to A2 F21. Okay, there's a very important conclusion called the reciprocity law. Which means if I know one view factor, F12, I can easily find F21 by using that equation. Now there's another law, the enclosure law. The general expression is that. Now, first of all, let's say it's only valid in an enclosure. So, enclosure. For instance, take this room. It's an enclosure. The front wall is 1, back wall 2, windows 3, halls 4, floor 5, ceiling 6. This room's a 6-surface enclosure. I'm going to write that for I equal 1. For each surface, I equal 1 to 6. So there could be 6 equations. I'll write one of them down. I'm going to let I equal 1. F11 plus F12 plus F13, F14, F15, F16 equal 1. I can write a similar equation for each of the 6 surfaces in this room. F21 plus F22 plus F23 plus F24 plus F25 plus F26 equal 1, and so on. I'm going to tell you what F11 is just a minute, okay? Let's just say, what is F12? Okay, I told you, the front wall is 1, the back wall is 2. F12 is the fraction of thermal radiation leaving the front wall that gets to the back wall. F16, the fraction of energy leaving the front wall that gets to the ceiling, wall 6, A6. Conservation of energy, okay? Enclosure law is conservation of energy. All the radiation leaving the front wall has to strike another wall in this room. And the total must be 100%. That's what the 1 stands for, 100%. So, there's our enclosure law. Now let's talk about FII equals 0 if surface is plane or convex. And then FII is not 0 if surface is concave. Plane surface. Radiation leaves the surface, we assume, like this. Does any part of the radiation end up striking the plane wall? I mean, is that legal? No, that's not going to happen. So any radiation leaving that surface will not hit that surface. Okay. Take convex. Take a small differential area up here. Will any of the radiation leaving that surface ever do this? No, that's illegal. Straight lines, straight lines. Conclusion, radiation leaving that surface will never hit that surface. FII is 0. Concave, small differential area, radiation leaves the concave area. But now, some of the radiation leaving the small differential area strikes the area. So FII is not 0 there because radiation leaving the surface can strike the surface. In words we say, the surface up here cannot see itself. The surface right here cannot see itself. Here the surface sees itself. The word see we relate to our eyes. Our eyes. If I put my head on this wall, and if I could get it right by the wall, do I see the front wall? Oh no, I don't see the front wall. Don't turn your eyes like that. I mean, I could. I still wouldn't see it. Conclusion, that surface does not see itself. I put on a surface like this now. Oh yeah, I can see my hands on both sides of my head. That's concave. That's why it's called the view factor, because it relates to what we see with our eyes, the view with our eyes. It helps us to see things. It helps us to see things. Okay, so another thing for an enclosure of n surfaces, there are n squared view factors. In this room, there may be 6 surfaces. How many view factors? 6 squared, 36. F51, F43, F26, F14, F35. I mean, it goes on and on. Okay, 36 different view factors. Now, some view factors are simple to find and other ones are more complex. Let's take some simple ones first. I'll take one that looks like this. Circular base, hemisphere above it. Circular base A1, hemisphere A2. We're looking at the inside now. N equal 2. Number of view factors. 2 squared equal 4. Here they are. Find them all. Okay. Take the easy one first. I think surface A1 is a plane surface. Yes, it is. Therefore, F1, 1 is 0 automatically. Got it. I think all the radiation leaving surface 1 is going to hit surface 2. Yeah, that's right. That's right. It will. All radiation leaving 1 will hit 2. Okay, 1. Now I'm stuck. I don't know F21. I don't know F22. I'm stuck, but now I use these guys. Oh, reciprocity. There we are. Reciprocity. F21 equal A1 over A2. F12. F12 is 1. A1 pi d squared divided by 4. Hemisphere pi d squared divided by 2, but it's divided by 2 for half hemisphere. So this is cancels, 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 cancels. And we have 2 divided by 4, 1 half. 1 half times F12 of 1. Got it. F22, enclosure law, 2 surfaces, n equal to F21 plus F22 equal 1. So F22, 1 minus a half equal a half. Got it? Okay, so that's called view factor algebra in a way. I said F12 is 1 by what rule? By observation. I mean, where else can the radiation go that leaves surface A1? There's no place else to go but A2. 100% of what leaves surface A1 ends up hitting A2 directly. Okay, by observation. Then we use reciprocity, relate those 2 guys. Then we use enclosure law to relate those 2 guys. Then we use this definition of a plane surface, F11 is 0. That's called view factor algebra. Now, a lot of times it's not that simple. A lot of times you have to go back to the basics and find these guys from that equation. So I'm going to show you how you do that. First of all, we can go to table 13.1. Yeah, table 13.1. Let's see here. These are 2D geometries. One, for instance, looks like this. There are 7 given in the table, 7 in the table. This is distance. I'm not going to do it that way. I'll do it this way. This is distance W. This is distance W. This is angle alpha. This is A1. And this is, I think he calls it IJ. AI, AJ. And then in the table, he says that Fij 1 minus sine alpha over 2. he has other geometries. Another one is two different diameter pipes. And like this is surface A2, and this is surface A1. And then he gives the equation for Fij, should be Ij. Table 13, 2. 3D geometries. First one, rectangles, one above the other. Separated by a distance L. And he gives us dimensions on those rectangles, X, Y, and L. So X and Y. This is I, this is J. And he gives us Fij. Oh, it's a big, long expression. It takes three lines in the table, 3 lines. Natural log, inverse functions, trig functions, things like that. It's pretty messy. The second one is 2 concentric circular discs separated by L. This one is Ri. This one is Rj. And he gives in the table Fij, the equation. And then he has 2 rectangles with a common edge. They're normal rectangles. So a right angle there. This is surface I, this is surface J, this is X, Y, and Z. And there's an equation given in that table, Fij equal, it's the longest equation of all, 4 lines of the equation. Okay. Those results came from solving this double area integral. Double area integral. It's really messy. It's really messy. Because it's a double area integral, so if you here's 1 and 2. So here's a little differential area 2. This is x2, and we call that z. This is dx2, dz2. And over here, here's a small differential area. And this one is dx1, surface 1. And this dimension is y, dy1. And here is r, and there is the angle theta 2, and there is the angle theta 1. Okay, now go ahead and find r in terms of those x1, y1, x2, z2. Go ahead and find cosine theta 1 in terms of the y's and the x's and the z's. This thing becomes humongous, humongous. You've got 4 integrals, integral with respect to x1, y1, x2, z2. Oh yeah, for one of the simplest possible geometries, the front wall and the floor. 2 rectangles, a common edge at right angles. It's a real tough job, a real tough job. Obviously, we don't do this in ME 415. We save that for the graduate students. They're the ones we love, you know. Make them work hard. So if you take the graduate course here in radiation, you'll probably do one of these in your life. I mean, at least one in the course. They'll make you do one because they want to make you see how tough it really is for simple geometries. So yeah, we're not going to do that though. Here are the results done for you. The results are real long equations, real long equations. But the good news is he's also given us graphical solutions. So if you want, you can do the graphical solution. I'll just put a couple on here. I'll put this one on here for you. This is Fij. Okay, and this goes from, let's see, that's figure, I'll put the figure down, figure 13.5. This one is figure 13.4. This one is figure 13.6. Okay, the x-axis, L over Ri. Y-axis, Fij. Parametric curves, they go up to 1, 0. X-axis, logarithmic, 1/10, 1, and 10. Curves look something like this. If you go in that direction, this parameter increases. That parameter is Rj over L. So, choice, the equation in table 13.2, or the graph, figure 13.5. Same thing for the parallel rectangles or the rectangles common edge at right angles. Okay, so you've got those in your library. That's what you use to solve this stuff if you can't see it. Over here, this problem I worked, I didn't need to go over there because I said, and here's the magic word, I said, I know F12 by observation. Without that, I'd be stuck. Okay. All right, now we take another one. We take and put a tennis ball inside of a basketball. Two spheres. Tennis ball inside a basketball. This surface, A1. This surface, A2. And now we say, find all F's. Okay, F11, F12, F21, F22. There are no plane surfaces. No. There's a convex surface. A1 is convex. F11 is 0. Got it. Now comes the by observation. You don't have to. You can do the enclosure law. F11 plus F12 equal 1. Conclusion? F12 equal 1. Okay, got it. Or you can say, if you want, by observation, all the thermal radiation leaving surface A1 ends up striking surface A2. Yeah, that makes sense. Now we're stuck until we use, okay, this is called view factor algebra. You use those algebraic equations, reciprocity, enclosure law. I say, okay, F21 equal A1 over A2, F12. F12 is 1. A1, surface area of a sphere, pi d squared. Pi d1 squared, pi d2 squared, times 1. d1 over d2 squared. So there's F21. Now I use the enclosure law. Got it. Enclosure law, F21 plus F22 equal 1. So F22. There it is. Found all 4 view factors. Of course, you find the view factors you need to solve the problem. Sometimes you don't need to find all of them, but sometimes you have to find several. Okay, let's do another simple one. This guy right here again, one more time. Except now we divide it up into 2. A1, A2, A3. N squared equal 3 squared equal 9 F's. Sometimes it pays off if you list them like in a matrix type format or determinant. For instance, F11, F12, F13. That way you don't forget anything. And it helps you too, it guides you. F21, F22, F23. F31, F32, F33. The name of the game, find all the view factors. Find all the view factors. 9 of them. Take the easy guys first. Are there any plane or convex surfaces? Plane or convex? Yep. A1, A2. Conclusion. F11 is 1. F22 is 1. Not F33. That's a concave surface. Take the easy ones again. I'm sorry? Oh, yeah. How about 0? Thank you so much. How about the radiation leaving A1? Can any of it get directly to A2? No. F12, 0. Can any radiation leaving surface 2 get directly to A1? No. A21 is 0. This is going pretty good. The enclosure law, F11 plus F12 plus F13 equal 1. Here's a rule. If I know any of these rows here, if I know everything except one F, I can solve for that one F by saying F21 plus F22 plus F23 equal 1. So what's F13? That's easy, it's 1. What's F23? That's 1. You want to talk about energy? Okay, look up here. All the thermal radiation leaving surface 1, can any of it strike A2? No. Therefore, where does it all go? To A3. Any radiation leaving A2, can any of it strike A1 directly? No. So where does all of it go? To A3. Now, don't play this game. Of all the radiation leaving A3, does half go to A2 and half go to A1? Oh, no, not there. Because some radiation leaving my fingertip here is going to hit over here. So F33 is not going to be 0. Okay, so stop. Now we're done. That was the simple stuff. Let's look at F31. F31, F13, reciprocity. A3, let's do it this way. F13, F31, pardon me. F31. A3, A1, F13. A1, half of a circle, pi d squared divided by 4, so pi d squared divided by 8. A3, hemisphere, area of a sphere, pi d squared. Hemisphere, pi d squared divided by 2. F13, I found it, 1. Pi cancel. D squared cancel. 2 divided by 8. 0.25, yeah. Then I say, you know what? By symmetry, F31 has to be equal to F32. So F32. How? Symmetry. Now I say, okay, now I know everything in the third row except one view factor. I don't know F33, but I do know F32 and F31. So I say F31 plus F32 plus F33 equal 1. So got it, done. Found all 9. Did I need to go to the figures or the tables? Nope. Why not? Because I said right here, oops, right up here, okay, F13 was 1. F23 is 1. That was what I had to say to make this thing work. Okay, now we'll try this one. Circular cylinder. Okay, it looks like this. This dimension, diameter, is 4 meters, separated by a distance of 1 meter. I call this surface A1, this surface A2, and the side walls are A3. Why do I call them different areas? Probably they have different temperatures. So maybe the temperature of A1 is 1,000, the temperature of A2 500, and the temperature of A3 300. So typically that's how you number surfaces. They have some differences. One might be adiabatic, one might be a known temperature. So you give it a different area designation, A1, A2, A3. I'm not going to. This guy's connected, it's not a dash line. It's a coffee can. The top is A2, the bottom is A1, the side walls are A3. You see, we're not calculating heat transfer yet. The first step in these problems is you calculate the view factors. Once you get the view factors, then you can find the heat transfer. But you can't find the heat transfer until you find the view factors. I might say, what is the net heat transfer between surfaces 1 and 3, the bottom and the sidewalls? The first thing I need is F13 to do that, F13. All right, so here we go again. How many surfaces? 3. How many view factors? All right, n squared, 3 squared, 9 F values. So 9 Fs, write them down. Okay. Now, look at that and say, okay, are there any gimmies? Oh yeah, there's 2 of them there. I see 2 plane surfaces, A1 and A2. Okay, so A1, F11, doesn't see itself, 0. F22 doesn't see itself, 0. Not A3, it's concave. A3, concave. Okay. Do I see anything by observation? A number, give me a number. No, I don't. Not like over here. Observation, the number is 1. Over here, F12, observation is 1. I see it. Over here, no, I have no idea. But luckily, if I go to these tables, table 3.2, oh, there it is, 2 parallel discs right there, same radius. Or if I want, there it is right there on a graph, figure 13.5. Okay, so I'm going to find F1 to 2, bottom to top. So I'm going to use, I'm not going to do the long equation, I'm going to use figure 13.5. First thing you do is you say, okay, that means I equal 1, J equal 2. So R, I, R, J, and L. L is 1 meter. the radius 2 for each one. Okay, find the x-axis, L over R1. Find the parametric variable, Rj over L, R2 over L. Go to the graph. X-axis, well, first of all, get rid of a lot of these lines. Go to 0.5 on the x-axis. Go to the line, or interpolate if you have to, you might have to find the line labeled 1. Go across horizontally and get the estimate of the view factor, 0.62. So F12, 0.62. Oh, did I? Oh, R2, what is R2? 2, and what's L1? Yeah, R2, diameter's 4, radius is 2. Did I miss? Oh, no. R2. L is 1, L is 1, R1, R2. Oh, no, yeah, thanks. Yeah, that's the new math, okay? Thanks, yeah. Okay, it's easy to do on the board, see, all I do is I get this magic finger that just does that, so if you used ink on your notes, you're in trouble, I guess, but that's okay. The answer is still 0.62. Thanks, though, I appreciate that. Okay, so what's the difference now? We couldn't use by observation. We had to use the tables, 13.1 or 13.2, or the figures. Don't forget now, two-dimensional means we've had it before for conduction, but just to remind you. Here it is. The bottom surface here is A1, the top surface here is A2, and the angle between them is alpha. The sides are W, W here, W here. How long is it? The answer is, I don't know. It's long, though. It's long compared to W. It's long. If it's long, you can say, oh, it's a 2D geometry, but you got to say the word long, okay? Here's two pipes carrying a hot fluid to cold fluid in a plant, hung from the ceiling. And I want to find radiation from one to the other, or maybe outside the space station, pipes carrying fluids, maybe for a solar thermal plant. It's a vacuum out there. I want the radiation exchange, hot to cold. Here's a 2D. That works fine as long as these cylinders' diameters are small compared to the length of them. So that's what 2D means, as we know from the conduction chapters. Okay, back to here. You know what? I think F12 is the same as F21. Turn the coffee can upside down. Does it matter? No. Oh, okay. That's also F21. Put a check mark by him. I got F12, I got F21. Good. Why is that? I don't know. Call it symmetry. Okay. I told you the rule. If you see any row, every row is the enclosure law. If you see any row where there's only one unknown, you can solve directly for that unknown. That's why it's good to put it in this format, like this. Oh yeah, F110, F12.62 plus F13 equal 1. So F13. This guy, 0, this guy, 0.62. So F13 must equal 0.38. Got it, F13. You know, if that's F13, I think that's the same thing as F23. Why shouldn't it be? Why? Well, it's symmetrical. Got it. F13 equal F23. Got it. I got 6 of the 9 now. Got 6 of the 9. Over here. Gee, I don't know any of these guys here, but oh yes I do. F31, F13, reciprocity. F31 equal A1 over A3, F13. Okay. A1, pi d squared over 4. Pi d squared over 4. Divided by A3, pi d times L. L is the spacing. L equal 1 meter. Like the picture in the textbook shows, L is the spacing from the two parallel discs. Times F13, I just found F13, it's 0.38. Pi cancels, pi cancels. We have 4, d. We have d over 4L. What's d? 4. What's L? 1. 4 divided by 4 times 1? 4 divided by 4 times 1? It's 1. 0.38. I got F31. Then I say to myself, gosh, you know what? I really think F31 is the same as F32. I say, how do you know that? I say, it's symmetrical. You got it. This is F32. All right, I got F31, F32. Here's the rule. On any row, when you put them in that format, if you don't know one F in a row, you say, F is enclosure law, F31 plus F32 plus F33 is 1. F31 plus F32 plus F33 equal 1. From there. F31, 0.38 minus 0.38, F33. F33, 0.24. Got it. I found all 9. Okay, that's how you play the game. You try to see if you can see things directly by observation. If you can't, you try and find either a table or a figure to find that first one that you need. And once you find that one, generally things start to fall out. Once I find F12, bam, 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 and I got everything right from there. That's all I needed. Okay, that's called view factor algebra. View factor algebra. I'll do one more because this is the one that confuses people. I'm going to take this bottom one down here. And I'm going to take an enclosure, which is a rectangular wall room. I'm going to call this area 1 and this area 2. And I want to, okay, I'll put some dimensions in here. I'll call that 2 centimeters, 3 centimeters, and 5 centimeters. And I want to find F12. Okay, it's like the ceiling would be A1 and the front wall is A2, just so you kind of know what it looks. This is a rectangular shoebox, this room is. Ceiling is A1, front wall is A2. To do this right, and here, let's draw the graph. Okay, so here's the graph. And we've got, okay, I'm going to draw the picture first on the graph. It looks like this. Right angle, I and J. X, Y, Z. And here's Fij. And the x-axis is Z over capital X. And the parametric curves are Y over X. And of course, in your data package for the course, you have table 13.1, table 13.2, all 3 of those figures, 4, 5, and 6, 13, 4, 5, and 6. You have all that on your data package. Okay, so here it is, F12. Sometimes this kind of gets people all messed up because 1 and 2 don't look like I and J over here. So you don't want to make a silly mistake on exam or homework. So the first thing you do, you say, okay, what do I want to call I? Okay, obviously I is the first subscript. 1. What is J? Okay, next thing, J, second subscript, 2. Here comes the tough part. This is the one where people generally make their mistakes with X, Y, and Z. And of course, it's going to give you an error in F12 when you do that. Okay, identify I. Here, that's AI. There's AJ. What's the common edge? X. Common edge, 5. For AI, what's the direction from the common edge away from there? 3. For J, what's the distance away from the common edge? Right. That is the Y is our Y goes with I, and I is this. That's 3. And J is 2. Yeah. There's the common edge right there. That's X. The distance away from the common edge for surface I is Y. I is 1. This is Y. And this is Z. Oh yeah, under stress, people do sometimes make silly mistakes. And that's the graph that separates the knows from the don't knows. You pretty much, it's tough to go wrong on this graph right here. I know where 1 and 2 are, believe me. Up here, I'll know 1 and 2, believe me. Down here, in a rectangular shoebox type of a situation, sometimes it's tough to find that I, J, X, Y, and Z. And that's why I want to make sure you knew how to read that graph well. Okay, we've got a good stopping point here. We'll pick it up. No homework's due on Monday. Next homework says due